This is nature at its most unforgiving, a force that can tear apart entire cities, drown continents, and erase thousands of lives in a single night. A world that burns, freezes, and rebuilds itself over and over again. From the birth of a hurricane in the silent skies above Africa to the unimaginable age when our planet froze solid from pole to pole, science has been chasing one question that transcends time. How does nature create destruction so vast, and yet, within it, the seeds of renewal? Every year, somewhere across the globe, satellites watch as new storms are born. They begin as invisible whispers in the air, small ripples in the atmosphere that grow into vast spiraling monsters. Each one is a living engine of wind, heat, and fury, feeding on the ocean's warmth, sculpting coastlines, and rewriting the lives of millions. And yet, hurricanes are only one face of Earth's temper. There was a time, long before the first city or the first name given to a storm, when our planet itself nearly died. 650 million years ago, ice crept from the poles to the equator, sealing the oceans, smothering the continents, and locking Earth inside a frozen tomb. Scientists call it Snowball Earth, the most extreme climate catastrophe in our planet's history. The story of hurricanes and ice ages is not one of isolated events. It is the story of energy, how it moves, transforms, and rebels. Every gust of wind, every drop of rain, every snowflake that falls is part of an ancient rhythm that governs the planet. For centuries, we have tried to decode this rhythm, from the fragile instruments aboard weather satellites to the deepest ice cores drilled from the Antarctic. But the more we learn, the more fragile the balance appears. The same mechanisms that once froze the Earth or powered monstrous hurricanes are stirring again today. The oceans are warming, the atmosphere is thickening, and the storms, they are growing stronger. So, how does a storm begin? What invisible chain of events turns a breath of warm air into a wall of destruction? And could the same forces that once froze the world be waking once more? This is the story of science versus chaos, of the planet's eternal struggle between fire and ice. From the tropical fury of hurricanes to the frozen silence of Snowball Earth, this investigation uncovers the anatomy of our planet's most violent transformations and the clues they hold for our future. Welcome to Anatomy of Extremes, When the Planet Fights Back. Part 1. The birth of a storm high above the sands of Africa. A pulse of heat begins to rise. It's nothing extraordinary at first, just warm air climbing from the Sahara, stirred by invisible winds. But in this simple act, something monumental is born. A storm begins to breathe. Every year, over 80 tropical systems form across the globe. Most vanish into open ocean, forgotten by all but satellites. Yet, a few evolve, growing larger, stronger, more organized, until they transform into one of nature's most powerful creations, the hurricane. The story of a hurricane begins thousands of miles away from the coastlines it will one day devastate. It starts with heat, relentless, shimmering heat radiating from the vast Sahara Desert. As the sun beats down on the desert floor, the air above it warms rapidly, rising and expanding. This creates waves in the atmosphere, ripples that drift westward into the Atlantic. Meteorologists call them African easterly waves, invisible seeds of chaos carried by the trade winds. For thousands of years, these waves have crossed the continent, spawning countless tempests. But it wasn't until the satellite age that scientists could finally see them form. From 22,000 miles above Earth, images reveal clouds gathering along a faint line of disturbance, like an idea taking shape. Within these clouds, thunderstorms begin to pulse and merge. Pressure drops. Winds accelerate. The rhythm of rotation begins to emerge. Chris Landsea of the National Hurricane Center describes it as a kind of atmospheric genesis. The moment the storm starts to live, when wind speeds reach 23 miles per hour, the system earns its first title, a tropical depression. From that point, every hour matters. At the National Hurricane Center, computers track each developing storm with precision that borders on obsession. They watch for changes in pressure, temperature, and humidity, the earliest signs of something dangerous. But even with modern technology, predicting which disturbance will grow into a killer remains one of meteorology's greatest challenges. Satellite data tells scientists what the storm looks like from above, its shape, size, and motion. But the truth of what's happening inside the storm lies hidden in the clouds. To find it, someone has to go in. That's where the hurricane hunters come in. Pilots who fly directly into the heart of developing storms. Their aircraft, the Lockheed WP-3D Orion, is less a plane and more a flying laboratory. Every inch of it bristles with instruments, Doppler radars, data probes, pressure sensors. As they descend toward the Atlantic, they fly through sheets of rain and turbulence so violent it feels like flying through war. Jim McFadden, one of the veterans of this dangerous mission, puts it simply, if you want to know a hurricane, you have to meet it face to face. At 5,000 feet above the waves, they release a dropsonde, a small probe that parachutes through the storm, transmitting data twice per second. Temperature, humidity, wind speed, and most importantly, atmospheric pressure. As the probe falls, scientists on the ground watch the readings appear in real time, the numbers dancing, shifting, and finally stabilizing. If the pressure continues to drop and the winds climb past 39 miles per hour, the storm earns its next title, a tropical storm. It receives a name, and with a name, it becomes history waiting to happen. But rotation alone doesn't make a hurricane. The storm needs fuel, and that fuel lies in the ocean below. The Atlantic's tropical waters, heated to over 80 degrees Fahrenheit, are an immense energy reservoir. Each molecule of water vapor rising into the air carries latent heat, a hidden form of energy released when the vapor condenses into clouds. As this heat spreads through the storm, it accelerates upward motion, feeding the very process that sustains it. The storm becomes a living engine, self-perpetuating, self-intensifying. Greg Holland, a meteorologist who has spent decades studying these storms, explains that the spin itself is borrowed from the planet's rotation, the Coriolis effect. It steals a bit of Earth's own rotation, he says, to give the storm its twist. In the northern hemisphere, this twist is counterclockwise. In the southern, clockwise. Without it, a storm would never sustain itself, the low-pressure center would simply collapse. With all the ingredients now in place, heat, moisture, spin, and low wind shear, the system begins to organize. Bands of thunderstorms wrap tightly around a central core. The pressure at the center drops further. The winds accelerate. At 74 miles per hour, the transformation is complete. The world now recognizes it by a single word, hurricane. At that moment, 200 miles across and climbing through the troposphere, the storm achieves both beauty and terror. From space, it is a perfect spiral, serene, almost divine in its symmetry. But for those below, it is the most violent machine nature has ever built. And yet, even now, it is only beginning to grow. Part 2. Inside the eye of the storm, the airframe shudders as the plane cuts into the storm's outer wall. Rain slams against the fuselage like gravel. Lightning flares white through the clouds, and the instruments flicker. The crew are strapped in, eyes fixed on the glowing radar display ahead. They're about to fly into one of the most violent places on Earth, the eye of a hurricane. For most of us, a hurricane is something we watch from a distance. A swirl on a satellite map, a headline warning on the evening news. But inside, it's another world entirely. A hurricane is not a single storm, but an intricate system of interlocking forces. Wind, heat, moisture, and pressure, all rotating around a point of impossible calm. The plane plunges deeper into the storm. Outside, sheets of rain fall so dense that visibility drops to zero. The radar shows bands of thunderstorms spiraling around the center like arms of a cosmic vortex. These are called rain bands, immense columns of rising air that carry moisture upward, where it condenses and releases heat. Each pulse of heat makes the storm spin faster, feeding the hurricane's central engine. We usually pick our way through the rain bands, says pilot Jim McFadden, his voice steady despite the turbulence. We try to avoid the most violent updrafts. But eventually, you have to head straight toward the eye wall. The eye wall, the fortress of cloud that circles the storm's heart, is where the hurricane reaches its peak fury. Winds here can exceed 200 miles per hour. The rain is horizontal. The updrafts are so strong that they can lift water, birds, even aircraft debris miles into the air. Meteorologist Robert Rogers calls it the pistons of the heat engine, where warm, moist air rises and releases its energy, powering the hurricane's entire circulation. Then suddenly, everything changes. The plane bursts through the eye wall into sunlight. The turbulence vanishes. The rain stops. For a few surreal moments, the crew are floating inside the eye, a vast, circular chamber of eerie calm. Below them, the ocean churns violently. Around them, a wall of cloud towers 10 miles high, its edges glowing in the sun. Above, a flawless blue sky stretches into the stratosphere. You look around, McFadden recalls, and it feels like you're inside a gigantic stadium. The walls are clouds, the floor is the ocean. It's breathtaking and terrifying. The eye is the hurricane's core, its axis of rotation. Here, the air is sinking instead of rising, warmed by the heat released in the eye wall. That sinking air creates a pocket of stillness, a calm that can mislead anyone who stands in its path. Many who survived the first half of a hurricane's strike once thought it was over, only to be caught in the returning winds when the other side of the storm arrived. From this rare vantage point, scientists collect their most valuable data. The crew releases a dropsonde, a small cylindrical probe that parachutes through the eye, measuring temperature, humidity, wind, and pressure. As it falls, it sends a stream of numbers back to the aircraft, each one helping to map the storm's anatomy. Pressure, in particular, tells the story. The lower the pressure in the eye, the stronger the storm. When the pressure falls dramatically, the air outside rushes inward faster and faster, spinning harder as it nears the center. This is why a hurricane's most intense winds are found just outside the eye, within that narrow ring of chaos. As scientists watch the probe's data scroll across their screens, they notice something else. The eye is shrinking. This is the hurricane's most dangerous phase, eye wall replacement. As the eye contracts, its rotation accelerates, like a figure skater pulling in her arms. The winds surge, the storm intensifies. It's a pattern meteorologists know too well. In 2005, Hurricane Wilma stunned researchers when its central pressure plunged to 882 millibars, one of the lowest ever recorded in the Atlantic. Its eye shrank to a mere 2 miles wide, and its winds roared to 185 miles per hour. From space, it looked almost perfect, a spinning pinhole of destruction. To the scientists inside their aircraft, the beauty was deceptive. Every reading they took meant that more lives were at risk somewhere below. A perfect storm is not a triumph. It's a warning. Each hurricane is classified by its maximum sustained winds, measured over 1 minute at a height of 33 feet. When a storm reaches Category 5, it becomes more than a weather event. It becomes a test of human endurance. From the calm of the eye, McFadden and his team turn their aircraft around, preparing to cut through the eye wall a second time. They know what awaits: turbulence, lightning, chaos. But without their work, the data that could save thousands of lives would remain hidden inside the storm. As they brace for impact, the pilot steadies his voice. "Hold tight," he says. "We're going back in." The engines roar. The plane dives into the wall of cloud once more, and the hurricane, alive, breathing, growing, spins on. Part 3. The science of destruction. Every hurricane is a riddle of heat, motion, and chance. To the untrained eye, it seems almost alive, a massive, breathing organism that grows, evolves, and dies. But at its core, it is pure physics: air pressure, energy transfer, and rotation working together in one colossal feedback loop. Understanding that loop is the holy grail of meteorology. If scientists can decode how a storm draws energy and where it releases it, they might one day predict how powerful it will become and where it will strike. For now, that prediction is still more art than certainty. To begin, Everything hinges on heat exchange, the invisible transaction between sea and sky. As sunlight warms the ocean's surface, trillions of molecules of water vapor rise into the air. Each droplet carries stored energy, known as latent heat. When that vapor condenses into clouds, the heat is released, warming the air around it. The warmer air then rises faster, drawing in more air from below, which, in turn, pulls in even more moisture. It's a chain reaction, and it doesn't stop until something interrupts it. In essence, a hurricane is a heat engine powered by the ocean. The greater the sea's warmth, the stronger the engine. When ocean temperatures cross 80 degrees Fahrenheit, about 27 degrees Celsius, the process accelerates dramatically. The storm feeds on the warmth below, converting it into kinetic energy, the energy of wind. Meteorologist Greg Holland describes it like fueling a machine. It's like filling your car with gasoline, he says. The warmer the water, the more fuel you have, and the farther the engine can run. But there's a delicate balance at play. If the atmosphere above is too dry, the rising air cools too quickly and the storm suffocates. If winds at high altitudes shear across the storm, moving in a different direction from those near the surface, the system's structure collapses. Scientists call this wind shear, and it's one of the few natural defenses against hurricane formation. When shear is low, the storm's tower of thunderclouds can rise undisturbed, reaching heights of 10 miles or more. Inside this tower, energy cycles continuously. Warm air rises, cool air sinks, moisture condenses, heat is released. This vertical circulation is the beating heart of a hurricane. But the mystery lies not in how hurricanes form. Scientists understand that part fairly well, but in how they intensify. Why does one storm remain weak while another suddenly explodes into a monster overnight? Dr. Joe Seon of the Hurricane Research Division believes the answer lies in the lowest layer of the atmosphere, the boundary layer where the ocean and air meet. That's where the real energy transfer happens, he says. It's the skin of the planet, and it decides how much power a storm can take in. To study this invisible frontier, researchers have risked their lives. In 2003, as part of Project Sea Blast, Hurricane Hunter aircraft flew into Hurricane Isabel, not at the usual 5,000 feet, but just 200 feet above the ocean's surface. Below them, 40-foot waves exploded against the wind. Salt spray coated the engines, nearly stalling them midair. One engine failed completely. Somehow, the crew managed to limp back to base, but the data they brought changed hurricane science forever. The results showed that as wind speed increases, the transfer of heat and moisture between the sea and the air rises exponentially. Each gust pulls more energy from the ocean, feeding the storm's acceleration. In short, a hurricane that's already strong finds it easier to get stronger, a terrifying feedback loop of self-amplifying force. Yet, even with this knowledge, predicting when that runaway intensification will occur remains elusive. The ocean isn't uniform. Beneath its surface lie swirling eddies, hidden pools of warmer water that act like turbochargers. When a storm passes over one, it can erupt in strength almost overnight. Meteorologists fear these moments the most. It's the nightmare scenario, says Seon. People go to bed expecting a Category 1 storm and wake up facing a Category 4. In 2005, that nightmare became reality. A modest hurricane crossed the Gulf of Mexico and encountered a deep pocket of warm water known as the Loop Current. Within hours, its wind speed skyrocketed. Its name was Katrina. The physics that drive such explosions are unforgiving. Warm water evaporates, moisture condenses, heat releases, winds rise, and the cycle accelerates. But for all its fury, the storm remains bound by simple laws of thermodynamics. It cannot create energy, it can only transform it. And when that energy source, the warm sea, is taken away, the storm begins to die. That's why landfall is both salvation and destruction. When a hurricane hits the coast, it loses its fuel. The ocean's warmth is replaced by dry land, friction, and cooler air. But in the few hours before it collapses, the storm unleashes every ounce of its remaining energy. For scientists, the goal is not just to understand these processes but to predict them. Faster computers and better models have cut track prediction errors by half over the last 2 decades. But intensity forecasts, how strong a storm will get, have barely improved. And that's where the next revolution in hurricane science begins. Machines that can enter the storm's deadliest zones without risking human lives. In a hangar in Florida, engineers prepare a small, sleek drone, the Aerosonde Mark III. Unlike traditional aircraft, this one has no pilot, can fly for 12 hours straight, guided by satellite, through the worst winds on Earth. It's designed to do what no human should, map the storm's heartbeat from within. When the Aerosonde first entered a tropical storm in 2005, scientists watched its data come in like signals from another world. It felt like watching a Mars landing, one researcher said. Except the planet we were exploring was our own. With each flight, humanity steps closer to solving the hurricane's greatest mystery. Not just how it forms, but why it becomes unstoppable. But even as our knowledge grows, the storms themselves are changing. The oceans are warmer now, the atmosphere holds more moisture, and each passing year, the engines of destruction spin a little faster. Part 4. The path of the storm. No force on Earth moves quite like a hurricane. It drifts, meanders, stalls. A 200-mile-wide giant steered by invisible hands. From space, it looks effortless, as if gliding over the ocean's surface with purpose. But beneath that elegance lies chaos. Predicting where a hurricane will go remains one of science's most confounding challenges. Each storm follows its own logic, obeying rules that shift with altitude, temperature, and time. In truth, a hurricane doesn't choose its path. It is carried, like a cork floating in a river, by vast currents of air that encircle the planet. These atmospheric currents are the trade winds, the jet stream, and high-pressure domes like the Bermuda High. Together, they form an intricate network of motion that can steer a hurricane thousands of miles, or trap it in place long enough to devastate a single coastline. Meteorologist Greg Holland explains it this way: a hurricane doesn't know where it's going. It's at the mercy of the air around it. It's like a leaf spinning in a stream, except the stream itself is constantly changing direction. In the tropics, the dominant winds blow westward. That's why most Atlantic hurricanes begin off the coast of Africa and travel toward the Americas. Pushed by the trade winds, they move at speeds of 10 to 20 miles per hour, slow enough for satellites to track, but fast enough to outpace human preparation if they suddenly change direction. And they often do. Looming over the Atlantic is the Bermuda High, a massive dome of high pressure that acts like a steering wheel. When it sits farther east, hurricanes curve harmlessly into the open ocean. But when it drifts west, it can push storms directly into the United States. Tiny changes in its position can mean the difference between a close call and a catastrophe. That's why meteorologists track not just the hurricane itself, but the entire atmospheric environment around it. Wind speed, pressure gradients, and temperature fields stretching across continents. They feed this data into computer models, mathematical simulations that try to predict how these systems will evolve. Each model is a different interpretation of the atmosphere. The American GFS model, the European ECMWF, and the British UCMET each runs billions of calculations every day, projecting the storm's future minute by minute. The results appear as colored lines on a map, known to meteorologists as spaghetti plots. Each line represents a potential path, and when those lines diverge, uncertainty reigns. Sometimes the models agree, more often they don't. In 2017, when Hurricane Irma barreled across the Caribbean, one model predicted a direct strike on Miami. Another showed it veering toward the Gulf of Mexico. The reality was somewhere in between, and millions of people evacuated based on shifting forecasts that changed by the hour. The truth is that even with modern satellites and supercomputers, predicting a hurricane's exact path is an act of controlled chaos. The atmosphere is a system of near-infinite variables. A small fluctuation in wind speed, even a single degree of temperature difference, can shift a storm's track by hundreds of miles. Dr. Robert Rogers of NOAA calls it the butterfly effect, scaled up to planetary size. But while predicting the storm's track is difficult, predicting its impact is even harder. What matters most is not just where a hurricane goes, but how it interacts with the land and sea as it approaches. Coastal shape, ocean depth, and even the time of day can amplify or reduce destruction. One of the most deadly outcomes of this interaction is the storm surge, the wall of seawater pushed ahead of a hurricane by its winds. When this surge hits shallow coastlines, it can climb 20 feet high and sweep miles inland. In 2005, Hurricane Katrina's surge reached 27 feet along parts of the Mississippi coast, submerging entire neighborhoods. 90% of hurricane fatalities come from drowning, not wind. Oceanographer Stephen Baig describes the phenomenon as the ocean rising to meet the storm. As the winds rotate counterclockwise in the northern hemisphere, they pile up water on the right side of the storm's path. That's why a city located just east of landfall often faces the worst flooding. When Katrina approached New Orleans, scientists at the National Hurricane Center saw the danger coming. The Bermuda High had shifted west, steering the storm directly toward the Louisiana coastline. The curvature of the Gulf funneled the surge straight toward the city's fragile levees. The warning signs were unmistakable and terrifying. At 6:10 a.m. on August 29, 2005, Katrina made landfall as a Category 5 hurricane. Winds screamed at 175 miles per hour. Within hours, the levees failed. The city drowned. More than 1,500 people lost their lives, and the cost of the disaster exceeded $100 billion. For meteorologists, Katrina became more than a tragedy. It was a lesson in humility. Nature had revealed how small our predictions still are, how a storm born as a whisper of warm air over Africa could become a catastrophe half a world away. Today, new generations of scientists are rewriting the equations. Using machine learning and real-time satellite data, they're teaching computers not just to calculate, but to learn from each storm. The goal is simple: forecasts that don't just predict where a hurricane will go, but what it will do. Because sometimes, the real danger isn't where the storm hits. It's how it behaves once it's there. Will it stall, dumping weeks' worth of rain in days? Will it surge inland? Will it weaken? Or will it strengthen again after landfall, feeding off swamps and marshes like the Everglades? History has shown that the path of a storm is never a straight line, neither across the ocean, nor through the human story that follows. For those who track them, every storm is both a mystery and a mirror, reflecting the fragile balance between the forces of nature and the limits of our understanding. Part 5. Landfall. When the SEA attacks, there is a moment, just before a hurricane makes landfall, when the world seems to hold its breath. The air feels heavy, electric. Birds vanish. The wind changes pitch, from a howl to a deep, rhythmic growl that rattles windows and bones alike. And then, in one violent instant, the ocean rises to meet the sky. This is landfall, the climax of every hurricane's life. It's where a storm born from sunlight and seawater meets the world we live in, and the results are nothing short of apocalyptic. From above, satellites capture the storm's final approach as a swirl of white spinning toward the coastline. But from the ground, it's chaos. Blinding rain, walls of wind, and a sea that no longer obeys gravity. Scientists call it storm surge, but the term hardly conveys its brutality. It's not a wave, not a tide. It's the ocean itself, lifted, shoved, and hurled inland by the hurricane's spinning winds. Under the right conditions, the surge can climb higher than a two-story house and rush inland for miles, swallowing everything in its path. Oceanographer Stephen Baig once described it as a slow-motion tsunami that never stops rising. In 2005, as Hurricane Katrina struck the Gulf Coast, the surge reached over 27 feet in parts of Mississippi. Entire neighborhoods disappeared. Concrete seawalls cracked like glass. In New Orleans, the city's levees, built to withstand almost anything, finally gave way. Within hours, 80% of the city was underwater. Mike Tice, A storm photographer who documented Katrina from a beachfront hotel remembers it vividly. The water came so fast, he said. It was like the ocean had leaped out of its bed. Cars floated past the lobby windows. Then one smashed through the glass doors, the horn blaring, lights flashing underwater. It was like a horror movie, but real. That single moment captures the cruel physics of a hurricane. The storm's right-hand side, where the winds rotate in the same direction as its forward motion, drives the water hardest against the shore. There, the surge becomes a weapon. Winds of 150 miles per hour push the sea ahead of them, piling it up higher and higher until it breaks across the land. Meteorologist Ivor Van Heerden explains, a hurricane is not just spinning, it's moving forward. So on one side, its rotation adds to its speed. On the other, it subtracts. That's why the right side of the storm is always deadlier. The winds and the surge work together, compounding their power. As the eye approaches, the winds grow stronger. The barometric pressure plummets. The air itself seems to roar, and then suddenly silence. The eye has arrived. For an hour or less, everything calms. Blue sky opens above the wreckage. Some people venture outside, thinking the storm is over. It's the cruelest illusion in nature, because what follows is worse. When the back half of the hurricane arrives, the winds shift direction, now blowing from the opposite side. The same surge that flooded inland is suddenly pushed back toward the sea, dragging homes, cars, and people with it. What the first winds destroyed, the second ones erase. Meteorologist Jay Barnes, who has chronicled hurricanes for decades, puts it bluntly, you survive the eye, you think you've made it, but you've only seen half the storm. As the eye wall sweeps over land, every element of the storm converges. Winds tear apart buildings, power lines snap, trees become missiles, debris caught in the storm's rotation slams into anything that stands. Windows implode under pressure differences. Roofs lift away like paper. At the University of Florida, researcher Forrest Master studies this chaos inside a vast wind simulator. An enormous machine powered by 8 industrial fans and a 5,000-gallon water tank. It can generate Category 3 winds and pounding rain. His goal, to understand how buildings fail and how to make them stronger. The key, Master says, is to test how every part of a structure, the roof, the walls, the windows, interacts under pressure. One weak link, and the entire building can come apart. In the simulator, a test window faces the storm. First, it holds. Then, as gusts rise and the pressure builds, the glass flexes, shatters, and the structure behind it collapses. Once wind breaches a home, internal pressure explodes outward, tearing the roof free and exposing everything inside. This chain reaction explains much of the devastation seen after landfall. One broken window can doom an entire house. One torn roof can unleash a neighborhood's destruction. And yet, the damage doesn't stop at the coast. The storm keeps moving, slower now, but still lethal. It drags torrential rain far inland, flooding rivers, breaking dams, and drowning cities hundreds of miles from the sea. The winds weaken, but the rain grows relentless. After landfall, the hurricane's energy begins to fade. No longer fed by the warm ocean, its vast heat engine runs dry. The eye collapses, the rotation breaks apart. Meteorologists call it decay, but for those beneath it, that word feels far too gentle. The truth is that a hurricane's death throes can be just as deadly as its peak. Tornadoes spawn in its outer bands. Rivers burst their banks. Electrical grids fail. And in its wake, a new disaster begins. Disease, displacement, and the long struggle to rebuild. When a hurricane finally dies, it leaves behind more than debris. It leaves data, the story of its life cycle encoded in pressure readings, satellite images, and wreckage patterns. Scientists gather this information like detectives after a crime, piecing together how the storm lived, grew, and died. Each one teaches them a little more and reminds them how little control humanity truly has. Every landfall is both an ending and a beginning. For the storm, It's the moment of final release. For us, it's the moment of reckoning. Part 6. The death and autopsy of a storm. When a hurricane dies, it does not vanish. It unravels. Its great spiral begins to lose symmetry. Its eye collapses into clouds, and its once roaring winds taper into a restless breeze. To the casual observer, it's over. But for scientists, this is when the most important work begins. They call it the autopsy of a storm. A hurricane's death is a slow and deliberate process. Not a single event, but a sequence of disconnections. As soon as it loses its fuel source, the entire atmospheric engine begins to fail. The warm sea that once fed it with vapor and heat is replaced by dry land. Friction increases. Moisture disappears. The storm's heart, its low-pressure center, weakens, and the whole system starts to decay from the inside out. Robert Rogers of NOAA describes it simply: once it hits land, the death warrant has been written. On land, the inflowing winds collide with forests, buildings, and hills, creating drag. The perfect circulation that once stretched for hundreds of miles becomes chaotic. The vertical column of rising air that powered the eye loses coherence, like a candle flame smothered by wind. The hurricane, deprived of its oceanic energy, releases more heat than it gains. Its internal balance collapses. What was once a single, unified engine fractures into disorganized thunderstorms and bands of rain. Still, even in its death throes, a hurricane can be deadly. The residual moisture and instability it carries can spawn tornadoes far inland, sometimes hundreds of miles from the coast. Rivers swell with the storm's leftover rain. Floods linger for days after the winds are gone. As the system finally breaks apart, meteorologists begin their analysis. They map its pressure readings, compare satellite images, and trace the sequence of its decline. Each storm leaves fingerprints, in the shape of its clouds, in the path of its debris, in the heat it leaves behind. The findings are entered into what researchers call a post-storm evaluation, an official autopsy report that records the hurricane's birth, growth, and death. These reports are not just scientific records. They are blueprints for survival. Each one helps refine models, improve forecasts, and understand the limits of prediction. But sometimes, the story of a hurricane's death takes an unexpected turn. Not all storms fade quietly. Some, even after making landfall, manage to revive briefly, violently, and mysteriously. In August 1992, Hurricane Andrew slammed into South Florida as a Category 5 storm, devastating entire neighborhoods. After 4 hours over land, it should have been finished. But as Andrew drifted westward over the marshy expanse of the Everglades, shallow, warm, and rich in moisture, something remarkable happened. The storm began to strengthen again. The Everglades acted like a wet lung, feeding the dying hurricane with just enough vapor to keep it alive. When Andrew reached the Gulf of Mexico, it found new fuel, warm, open water. Within hours, it was reborn as a Category 4 storm, battering Louisiana before finally dissipating for good. Meteorologists still debate why this happens. Some suggest that moisture-rich terrain, swamps, wetlands, or saturated ground can prolong a hurricane's life by maintaining its boundary layer. Others argue it's a trick of timing, a lucky alignment of temperature and humidity that allows the storm to draw a final breath before it collapses. Whatever the cause, these resurrections reveal just how fragile and unpredictable a hurricane's death can be. To scientists like Chris Landsea, each autopsy is a chance to see deeper into the storm's anatomy. By reconstructing the life cycle of past hurricanes, researchers can identify patterns, signals that reveal how storms form, strengthen, and die. This knowledge feeds into new forecasting models, reducing uncertainty and, ultimately, saving lives. Over the past 2 decades, improvements in storm tracking have been dramatic. Forecast errors for a hurricane's path have been cut nearly in half. But its intensity, how strong it will become, and how long it will last, remains far more difficult to predict. This challenge has taken scientists back to the start, to the fundamental question: What controls the energy exchange between sea and sky? To answer it, researchers turn again to technology: drones, satellites, ocean buoys, and supercomputers. The next generation of unmanned aircraft, like the Aerosonde and NOAA's new Altius drones, can fly directly into the storm's lowest layers, skimming just above the ocean to collect data from the most dangerous zones, the boundary layer, where heat, friction, and chaos collide. This is the region where hurricanes are born and where they die, a thin, volatile membrane between water and air that holds the secret to their power. The data these machines collect, temperature, humidity, turbulence, energy flux, are transforming our understanding of storms. With every mission, the models grow more precise. One day, forecasters hope, we will know exactly when and where a hurricane will explode into strength or collapse into nothing. But for now, the only certainty is that they will keep coming. The seas are warmer. The air holds more moisture. The boundaries that once limited these storms are changing. Every hurricane that dies leaves behind the blueprint for another waiting to be born. And as scientists close the book on one storm, the next one is already forming somewhere beyond the horizon. A small pulse of heat rising from the ocean, gathering strength, waiting for its turn to live. Part 7, Climate's Reckoning. Warming oceans and stronger storms for centuries. The rhythms of the sea and sky have governed the birth of hurricanes. Predictable, cyclical, almost ritualistic. Warm waters rise, winds spiral, storms form and fade. But now, those rhythms are shifting. The oceans are warmer, the air is thicker, and the planet itself seems to be rewriting the rules of the game. Scientists call it the climate signal, a slow, steady distortion of natural systems caused by the accumulation of heat in the Earth's atmosphere and oceans. It's not a new cycle, nor a temporary phase. It is a global transformation, and hurricanes have become its most visible messengers. Every storm begins as a transaction of heat. The warmer the ocean, the more energy available to power that transaction. In the last 50 years, the world's oceans have absorbed over 90% of the excess heat trapped by greenhouse gases. That heat doesn't vanish. It lurks beneath the surface, invisible but deadly, turning vast stretches of sea into liquid fuel for storms. Dr. Carrie Emanuel, a leading hurricane researcher at MIT, describes it as loading the dice. Warmer waters don't guarantee more hurricanes, but they do increase the odds that a storm, once formed, will grow into a monster. The atmosphere doesn't create more storms, he says. It just gives them more to feed on, and the results are already evident. In the 1970s, Category 4 and 5 hurricanes accounted for about 20% of all major storms. Today, they make up nearly 35%. The strongest hurricanes are getting stronger. Their rainfall is increasing. Their reach is expanding into regions once thought safe. Places like the North Atlantic, where temperatures were once too cold to sustain them. In 2020, Hurricane Delta reached Category 4 intensity in the Gulf of Mexico with astonishing speed, less than 36 hours from tropical storm to powerhouse. Meteorologists call this rapid intensification, a process once considered rare but now increasingly common. In the past 4 decades, the number of storms that rapidly intensify near land has doubled. This acceleration leaves little time for preparation. It's the new nightmare scenario, says Dr. Emanuel. Communities that once had days to prepare now have hours. The cause, scientists agree, lies in the ocean's upper layers, the thermocline, where heat is stored and mixed by currents. As this layer deepens and warms, storms can draw from an almost limitless reservoir of energy. Even after churning up cooler water from below, there's still enough warmth to keep them alive. But rising sea temperatures are only part of the story. The atmosphere itself is changing. A warmer atmosphere holds more moisture, about 7% more water vapor for every degree Celsius of warming. That extra moisture translates directly into heavier rainfall. During Hurricane Harvey in 2017, rainfall totals exceeded 60 inches in parts of Texas, the highest ever recorded from a single storm in the United States. Studies later showed that climate change made Harvey's rainfall 3 times more likely and 15% more intense. Then there's sea level rise. Since 1900, global sea levels have risen about 8 inches. That might sound small, but it amplifies storm surge dramatically. When a hurricane pushes water toward the shore, it starts from a higher base level, meaning flooding reaches farther and deeper than it once did. For coastal cities already sinking due to subsidence, this difference can mean the line between safety and destruction. New York learned this lesson in 2012 when Hurricane Sandy made landfall. Though only a Category 1 storm, its massive size and high tides created a surge that flooded lower Manhattan, paralyzing the world's financial center. It wasn't the wind, says oceanographer Philip Orton. It was the water, the slow, inevitable rise of the sea meeting the sudden violence of the storm. Sandy marked a turning point in how scientists and governments viewed climate risk. The once separate disciplines of meteorology and climate science began to merge. Short-term forecasts and long-term projections now inform one another, painting a single picture of a warming world spiraling toward volatility. But the deeper story is about energy, how much the Earth's systems can absorb before they break. Hurricanes are engines of balance. They move heat from the tropics toward the poles, distributing excess energy. In that sense, they are symptoms of a planet trying to cool itself. Yet, as greenhouse gases trap more heat, the system becomes overloaded. The storms grow stronger not out of malice, but necessity. This feedback loop, heat creating storms, storms redistributing heat, has defined the planet for millions of years. What's new is the human fingerprint. Every ton of carbon released shifts the baseline. Every degree of warming tips the scales toward chaos. And the projections are sobering. By the end of this century, scientists expect the frequency of Category 4 and 5 hurricanes to increase by as much as 25%. Rainfall rates may climb by 30% or more. Coastal flooding could become an annual occurrence in cities like Miami, Jakarta, and Lagos. In some regions, the danger isn't more storms. It's stronger ones forming in unexpected places. In 2022, a hurricane formed farther north in the Atlantic than any on record, driven by anomalous sea surface temperatures. Japan, Korea, and even the Arctic are now witnessing tropical systems in waters once thought immune. The climate signal is everywhere, written in rising tides, warped weather patterns, and the eerie resilience of storms that refuse to die. For those who study them, hurricanes are no longer isolated events. They are the pulse of a changing planet, a warning written in wind and water. And if the trend continues, the storms of the past may one day look small compared to those yet to come. Part 8. The Physics of the Planet. Earth's deep energy cycles. To understand the hurricane, you must first understand the planet. Because every storm, no matter how violent, is only a momentary expression of something far greater. The vast, eternal dance of energy that drives Earth itself. This planet is not still. It breathes, it pulses, it changes. From molten core to icy pole, from tropical sea to upper atmosphere, energy is constantly being absorbed, stored, and released. Hurricanes are simply one way the planet exhales. Dr. Richard Alley, a climate geophysicist, once put it this way: the Earth is a heat engine, and weather is the noise of that engine running. It's a powerful metaphor, but it's also physics. The same laws that spin a hurricane govern the flow of magma, the drift of continents, even the rhythm of ice ages. At the heart of it all lies one principle: energy seeks balance. The sun floods Earth with 173,000 terawatts of energy every second, more than 10,000 times the power consumption of all human civilization. Yet that energy is not distributed evenly. The equator receives far more heat than the poles, creating an imbalance that the planet constantly tries to correct. This imbalance sets the atmosphere in motion. Warm air rises, cold air sinks, and vast circulation cells, the Hadley, Ferrel, and polar cells, churn the skies like gears in an invisible machine. These atmospheric engines move heat poleward, just as ocean currents like the Gulf Stream do beneath the surface. Hurricanes form where these systems overlap. In the tropics, where the ocean's warmth fuels the air's ascent and the planet's rotation gives it spin. They are, in essence, pressure valves for a planet trying to even out its own temperature. When the system runs smoothly, storms come and go, heat is redistributed, and balance is restored. But when something interrupts the flow, when carbon traps heat, when the poles melt, when the oceans change their currents, the machine falters. Energy builds, and the planet, always seeking equilibrium, finds new, more violent ways to release it. That's why understanding hurricanes isn't just about predicting weather. It's about decoding how Earth responds to stress. Throughout history, the planet has gone through periods of massive imbalance. Times when the energy cycle broke down so completely that it transformed the entire climate. One of the most dramatic examples happened over 650 million years ago, during an era scientists now call Snowball Earth. Imagine a world encased in ice from pole to pole. The oceans sealed beneath frozen lids, continents buried beneath glaciers miles thick, sunlight reflecting off a white planet into space. For millions of years, the Earth was frozen solid. Not a drop of liquid water anywhere on its surface. Sounds like science fiction, yet the evidence lies in stone. Ancient rocks in Namibia, Australia, and Canada contain glacial deposits where tropical fossils should be, clear proof that ice once reached the equator. What could have driven such a catastrophe? The leading theory points again to energy balance. Around 715 million years ago, volcanic activity pumped carbon dioxide into the atmosphere. At first, it warmed the planet, but that warmth accelerated weathering on land, drawing CO2 out of the air and locking it into rocks. The greenhouse effect weakened, the atmosphere cooled, and the oceans began to freeze. As ice spread, it reflected more sunlight back into space, triggering a feedback loop known as ice albedo amplification. The more the planet froze, the colder it became. Eventually, Earth reached a tipping point, a runaway freeze from which there seemed no escape. For millions of years, the planet was silent, a global winter. Yet even then, its heat engine never truly stopped. Beneath the ice, volcanoes continued to erupt, slowly filling the atmosphere with CO2 once more. The greenhouse effect returned, melting the ice in a cataclysmic thaw that flooded continents and transformed the climate forever. This was nature's most extreme correction, a frozen reboot of the planet's energy system. To modern scientists, Snowball Earth is both a mystery and a warning. It proves that the planet's climate can flip from one extreme to another, from inferno to icebox, when its energy balance is pushed too far. Hurricanes and ice ages may seem like opposites, but they are twins in physics. Both arise from the same principle, imbalance. Too much heat, and the planet releases it violently through storms. Too little, and it traps it in ice. Both are symptoms of a system struggling to find equilibrium. Dr. Judith Curry, a climate dynamics expert, explains it simply: hurricanes are the weather of imbalance. Ice ages are the climate of imbalance. The difference is time. One lasts hours, the other lasts millennia. Seen from this perspective, every hurricane is a miniature echo of Earth's ancient turmoil. When a storm spirals across the ocean, it is replaying a pattern as old as the planet itself, the ceaseless negotiation between chaos and order. Today, that negotiation is once again under strain. The oceans warm faster than ever recorded. The polar ice retreats. The great currents that distribute heat, the Atlantic meridional overturning circulation among them, show signs of slowing. It's as if the planet's gears are grinding, searching for a new rhythm. And history suggests that when Earth's energy cycles shift, the consequences are vast. The next part of the story travels deep into time, to the frozen silence of Snowball Earth, when the world itself seemed to stop turning. Part 9, The Frozen World. Inside the age of Snowball Earth, picture the planet as seen from space, silent, gleaming, and white. From pole to pole, a solid crust of ice stretches unbroken across oceans and continents. The equator, once a band of blue and green, now mirrors the poles. No waves break, no storms rage. Even the clouds are thin, frozen specters drifting in a frozen sky. This was Earth 650 million years ago, a world entombed in ice, a planet that had, for a time, forgotten warmth. Scientists call it Snowball Earth, and for decades, they struggled to believe such a thing could be real. How could a planet orbiting a sun like ours ever freeze solid? The answer, as always, begins with imbalance. Before the freeze, Earth was hot, humid, and restless. Volcanic eruptions filled the air with carbon dioxide, trapping heat in the atmosphere. Oceans teemed with microbial life. Then, gradually, that balance shifted. Rain began to wash CO2 from the air, binding it to minerals on land. As weathering accelerated, greenhouse gases dropped. Temperatures fell, just slightly at first, but enough to trigger a chain reaction. As ice crept down from the poles, it reflected sunlight back into space, amplifying the cooling effect. This process, known as ice albedo feedback, is one of the most powerful feedback loops in climate physics. The more ice forms, the less heat the planet absorbs. The less heat it absorbs, the more ice forms. Once that feedback crossed a critical threshold, the transformation was unstoppable. Within a geological instant, perhaps a few thousand years, the Earth plunged into a global winter. Everywhere, glaciers ground across the continents. Oceans froze over, trapping life beneath a lid of ice hundreds of meters thick. The atmosphere grew thin and dry. Temperatures at the equator dropped to -40 degrees Celsius. From orbit, the planet must have looked like a single white marble spinning through the dark. Yet even in this silence, life endured. Beneath the frozen oceans, near volcanic vents and geothermal seeps, microscopic organisms clung to existence. Cyanobacteria, the oxygen-producing pioneers of Earth's early biosphere, survived in thin layers of brine trapped between ice crystals. In these hidden refuges, life persisted for millions of years. Geobiologist Gabrielle Walker calls this life's long breath, the quiet pause before the next great expansion. Evidence of that survival lies locked in ancient rocks. In Namibia and Australia, geologists have found cap carbonates, thick layers of limestone that formed immediately after the ice melted. Their presence suggests a sudden, global warming event powerful enough to end the freeze all at once. So how did the thaw begin? Deep beneath the ice, volcanoes never stopped erupting. They released carbon dioxide and methane into the air, gases that couldn't be absorbed by weathering because the land was sealed under ice. For millions of years, these gases accumulated, slowly rebuilding the greenhouse effect. Eventually, the atmosphere reached a tipping point. With CO2 levels perhaps hundreds of times higher than today's, the greenhouse effect roared back to life. Trapped heat began to melt the equatorial ice. As dark water emerged, it absorbed sunlight, accelerating the thaw. Within a few thousand years, the blink of an eye in geological time, the planet went from frozen silence to torrential warmth. The flood that followed reshaped the Earth. Oceans rose, carving new coastlines. Torrents of meltwater washed minerals into the seas, fueling explosions of life. It was a planetary rebirth and possibly the trigger for one of the most important chapters in evolution, the rise of complex, multicellular organisms. In that sense, Snowball Earth wasn't just an extinction, it was a crucible. The planet froze to the brink of death and thawed into new life. Dr. Paul Hoffman of Harvard University, who helped pioneer the Snowball Earth theory, once said, "It's the closest thing we know to a planetary resurrection." But the legacy of that deep freeze didn't end with the thaw. The cycles it revealed, the push and pull between greenhouse gases, sunlight, and ice, remain the foundation of Earth's climate system today. Every storm, drought, and hurricane still echoes that ancient rhythm. Heat trapped, released, rebalanced. And perhaps the most haunting truth is this: the same forces that froze the planet solid are now stirring again, in reverse. Today, instead of losing heat, Earth is trapping it. Instead of white ice reflecting sunlight, dark oceans absorb it. The feedback loop has flipped. Where once ice spread across the world, now warmth does. As scientists look at rising temperatures, melting glaciers, and warming seas, some have begun to see a disturbing symmetry. We may not be entering another Snowball Earth, but we are certainly entering another planetary experiment. One where balance is once again being tested, and no one can predict the outcome. Snowball Earth reminds us that climate is not fixed. It is an organism with moods, tempers, and memory, capable of changing not over centuries, but catastrophically, in the blink of geological time. The frozen world of the past stands as both a warning and a mirror. It shows us what happens when the planet's equilibrium is lost, and what it takes for life to find its way back. The question now is simple and terrifying. If the Earth could freeze itself solid, could it also overheat beyond repair? Part 10. The Thaw. How Earth came back to life for millions of years. Earth had been locked in silence. The world was white, barren, and still. No rivers flowed. No storms thundered. The oceans lay sealed beneath a fortress of ice that stretched from pole to pole. And then, one day, in geological terms, the ice began to crack. Deep beneath the frozen crust, heat had been gathering. Volcanoes, hidden under miles of glacier, continued to erupt, exhaling carbon dioxide into the air. But with no liquid water to dissolve it, the gas accumulated unchecked. Over millions of years, the concentration of CO2 rose to unimaginable levels, perhaps more than 1,000 times higher than today's atmosphere. Eventually, the greenhouse effect roared back to life. The sun's rays, once reflected harmlessly away by the ice, began to warm the atmosphere again. The planet had reached its breaking point. Dr. Paul Hoffman of Harvard describes it like a planetary fever. For millions of years, Earth was hypothermic. All its energy systems shut down. Then, suddenly, it spiked a temperature. The thaw began slowly at first. Equatorial ice, thinned by heat and darkened by volcanic ash, started to absorb sunlight instead of reflecting it. Pools of meltwater formed. Within a few thousand years, the process accelerated. A runaway chain reaction of melting, absorption, and warming. It was the mirror image of the freeze that had trapped the world so long ago. The same feedback loops that had plunged the planet into ice now worked in reverse. As the glaciers retreated, the oceans boiled with energy. Gigantic torrents of meltwater poured from the continents, carrying nutrients into the sea. Carbon dioxide, the gas that had saved the planet from its frozen death, now made it swelter. Global temperatures soared to tropical levels. In some places, the oceans may have reached 40 degrees Celsius, hot enough to kill much of the surviving microbial life. But from destruction came renewal. Those floodwaters carried with them phosphates, silicates, and other minerals that had been locked in the ice. When they reached the sea, they fertilized the ocean like a planetary bloom. Algae thrived, microbes multiplied, oxygen levels rose, and slowly, after hundreds of millions of years of stasis, life began to evolve again, this time into new, complex forms. The period that followed the thaw, known as the Ediacaran, saw the first appearance of multicellular organisms, soft-bodied creatures resembling jellyfish, worms, and fronds. It was as if the planet, having survived its own near-death experience, decided to create something entirely new. Paleobiologist Mary Drozer calls this the second Genesis. She explains, when Earth came out of Snowball, the oceans were infused with nutrients and energy. It was a perfect storm for innovation. Life had room to experiment. This biological explosion set the stage for everything that would follow. From the Cambrian explosion 540 million years ago, when complex animals filled the seas, to the eventual rise of vertebrates, plants, and much later, humans. The irony is profound. Without the Snowball Earth catastrophe, without that deep freeze and the violent thaw that followed, life as we know it might never have existed. Catastrophe, it seems, is not only destructive, it is creative. But while Earth found its balance again, the scars of that time remain etched in stone. In Namibia, cap carbonates, thick layers of limestone, mark the global flood that followed the thaw. Their chemical composition shows a sudden, massive influx of carbon into the oceans, confirming just how quickly the planet swung from ice age to greenhouse. It's a reminder that the Earth's climate is not a steady system but a pendulum, capable of swinging from one extreme to another with astonishing speed once its equilibrium is broken. Modern scientists studying climate change find uncomfortable parallels. Today, we are not cooling the planet, we are heating it. But the physics is the same: feedback loops. Where ancient ice once reflected sunlight, modern carbon traps it. Where volcanoes once flooded the atmosphere with greenhouse gases, now humanity does. And once again, the planet is responding, shifting, warming, searching for a new balance. The story of Snowball Earth and its thaw is not just history, it's prophecy. It shows us that the planet can endure extremes, but only by transforming itself in ways no species can control. For a brief moment after the thaw, Earth entered one of its most stable and fertile periods. The climate balanced, the seas teemed with life, and the planet breathed deeply again. But that balance, as history has proven, never lasts forever. Because Earth's energy machine, the same one that powers hurricanes, drives currents, and builds climates, never truly rests. It only waits for the next imbalance to awaken it. Part 11. Echoes Through Time. Linking ancient climate catastrophes to the modern era the Earth remembers. Every mountain, every layer of stone, every fossil is a record of what has been and what could be again. The deep freeze of Snowball Earth is not just a relic of prehistory. It is a message carved into the planet's memory. It tells us that when energy imbalances grow too large, the planet reacts violently, decisively, and without mercy. For most of human history, that lesson lay hidden beneath our feet. We lived in a narrow window of climate stability, a rare, fragile balance that lasted roughly 12,000 years, since the end of the last ice age. It was during this calm that agriculture was born, cities rose, and civilization flourished. We call it the Holocene, but in truth, it is an intermission between catastrophes. Now, that intermission is ending. Over the past century, the planet's temperature has risen faster than at any time in the last 10,000 years. The same forces that once plunged the Earth into ice are now driving it toward heat. Only this time, the trigger isn't volcanic or cosmic. It's human. We have become, in effect, a geological force. Every factory, every car, every power plant is a miniature volcano, exhaling carbon into the sky. The result is an atmosphere thick with heat-trapping gases, the same gases that once ended Snowball Earth. The difference is speed. What took millions of years to unfold during the Neoproterozoic era is now happening in less than 2 centuries. Dr. Richard Alley, the geophysicist who studies ancient ice cores, once said, "If you want to know what the future looks like, dig into the past, because the physics hasn't changed, and the parallels are haunting." During Snowball Earth, the planet's reflective ice sent sunlight back into space, plunging it into deep freeze. Today, the loss of ice at the poles has the opposite effect. Dark water and rock absorb heat instead of reflecting it, amplifying warming. The feedback loop has reversed direction, but the acceleration is just as unstoppable. The geological record tells us that once the planet crosses certain thresholds, change becomes nonlinear, fast, chaotic, and irreversible on human timescales. The ice sheets of Greenland and Antarctica hold enough frozen water to raise sea levels by more than 200 feet. Melt them and entire coastlines vanish. Meanwhile, the ocean currents that move heat around the globe, the same that gave birth to hurricanes, are slowing. Satellite measurements show that the Atlantic Meridional Overturning Circulation, AMOC, the Great Conveyor Belt of the North Atlantic, is weaker now than at any time in the past 1,000 years. If it collapses, Europe could cool even as the rest of the world burns. It's a paradox worthy of Snowball Earth itself. Warming that leads to freezing, balance lost in every direction. And yet, the echoes don't stop with physics. They reverberate through biology, politics, and culture. Just as the Great Thaw birthed new life forms, the changes we face today may force humanity to evolve. Technologically, socially, even morally. We are, in a strange way, standing at another planetary crossroads. The choices we make in this century will shape not only our climate, but our place in the geological record. Millions of years from now, a layer of rock may preserve our legacy. A thin band of plastic, soot, and carbon marking the arrival of the Anthropocene, the age of humans. Paleoclimatologist Katherine Hayhoe describes this moment not as a crisis, but as a negotiation between our species and the planet that sustains us. She warns that, like any negotiation, it has limits. You can't bargain with physics, she says. You can only respond, and that is what Earth demands now, a response. Because hurricanes are no longer just weather events. They are symptoms. Each one whispers the same truth. The energy balance is shifting. The same heat that once melted the world out of ice now fuels the storms that pound its coasts. The same carbon that once resurrected a frozen planet is now pushing ours toward fever. The difference between then and now is that this time we are aware. We have satellites, supercomputers, and models that can predict the future, but prediction is not prevention. Knowing the storm is coming does not stop it from forming. The story of Snowball Earth reminds us that the planet always finds equilibrium. But that balance doesn't have to include us. Still, the Earth's resilience offers hope. After every catastrophe, life returned. After every freeze or flood, the planet recovered. The question is whether we will still be here to see it happen. Some scientists believe we can steer the course through renewable energy, carbon capture, reforestation, and global cooperation. Others argue it may already be too late for reversal, and that adaptation is the only path forward. But both camps agree on one thing. The laws of energy that froze the Earth 650 million years ago are the same ones shaping our world today. Our fate, like that of the ancient microbes beneath the snowball ice, will depend on how well we can adapt and how quickly we can learn. Because in the end, the Earth will balance itself. The only question is, what will it look like when it does? Part 12. The Return of Chaos. Modern signals. Ancient patterns. The story is repeating itself. Slowly at first, almost imperceptibly, and then all at once. The signals are there, written across the oceans, the ice, the sky. Patterns that once shaped a frozen world are resurfacing, though in a new, inverted form. The Earth is once again out of balance. The signs began subtly. A small rise in ocean temperature, a thinning of polar ice, a slight shift in global wind patterns. At first, scientists thought these changes were noise, normal fluctuations in a vast and complex system. But now, the signal is unmistakable. The planet is warming, and the energy trapped within it is beginning to behave in ways both familiar and terrifying. It is, in essence, the return of chaos. In the ancient Snowball Earth, imbalance led to a freeze. Sunlight bounced off reflective ice, cooling the world into stasis. Today, the imbalance leads the other way. Excess heat amplifies itself. Instead of reflection, there is absorption. Instead of equilibrium, acceleration. This reversal is the mirror image of the past, a warm ball Earth in the making. Already, the patterns of instability are emerging. The jet stream, once a stable ribbon of wind that separated cold and warm air, is wobbling wildly, allowing Arctic air to plunge south and tropical heat to surge north. Weather systems that used to drift now stall, lingering for days or weeks over the same region. Floods, droughts, and heat waves overlap in ways no climate model of the 20th century predicted. Dr. Jennifer Francis, an atmospheric scientist who studies polar dynamics, explains it this way. The Arctic is warming 4 times faster than the rest of the planet. That disrupts the jet stream's flow, and once the air stops moving in smooth waves, chaos takes over. Hurricanes, too, are showing this signature of chaos. They move slower, rain longer, and grow stronger than ever before. In 2019, Hurricane Dorian stalled over the Bahamas for nearly 2 days, unleashing destruction on a scale unseen in modern history. In 2023, Typhoon Mawar sustained Category 5 intensity longer than any storm on record. These are not anomalies. They are warnings. Computer models once projected these kinds of events for the late 21st century. They are happening now. But perhaps the most profound echo of Earth's ancient imbalance lies not in the atmosphere, but in the ocean, the great regulator of planetary energy. For centuries, the Atlantic's vast conveyor belt, the AMOC, Atlantic Meridional Overturning Circulation, has moved warm water northward and cold water southward, maintaining the climate balance between hemispheres. It is, as some scientists call it, the planet's heartbeat. Now, that heartbeat is slowing. Measurements taken over the last 3 decades show a clear trend. The AMOC has weakened by about 15%, likely due to the influx of meltwater from Greenland's ice sheet. Freshwater, being less dense than saltwater, disrupts the sinking motion that drives the current. If it collapses entirely, Europe could enter a new ice age, even as global temperatures continue to rise. It sounds paradoxical, but it's perfectly consistent with the laws of planetary energy. Just as the ancient Earth's warming once led to freezing, today's heat could create localized cold. The balance swings wildly before it settles, if it ever settles. In the Pacific, a similar pattern emerges. Marine heat waves, vast blobs of warm water stretching thousands of kilometers, are reshaping ecosystems, killing coral reefs, and redirecting storm tracks. Scientists tracking the phenomenon have begun to use new language to describe it: climate turbulence, energy chaos, Earth system instability. To some, it feels like the planet is entering a new phase, a dynamic state where old rules no longer apply. Dr. Johan Rockström of the Potsdam Institute for Climate Impact Research warns that we may be nearing multiple tipping points, irreversible thresholds that, once crossed, trigger runaway feedbacks. Among them, the collapse of major ice sheets, the thawing of permafrost, releasing trapped methane, the death of the Amazon rainforest, the slowdown of ocean circulation. Each of these, on its own, would alter global climate. Together, they could reshape the planet entirely. We're approaching the edges of the safe operating space for humanity, Rockström says. Beyond it, the Earth becomes self-reinforcing and unpredictable. In this light, the hurricanes, droughts, and melting ice of today are not isolated events. They are signals, fragments of a much larger transformation unfolding beneath our feet. A transformation eerily reminiscent of past global resets, like Snowball Earth. But there is a crucial difference. This time, we are here to witness it and to influence it. Unlike the microbes that survived the ancient freeze, we have tools, data, and foresight. We can measure the chaos as it unfolds. We can see it coming. Yet, awareness alone is not enough. The planet is not waiting for us to act. As energy accumulates in the system, Earth will find ways to release it, through storms, floods, heat waves, or other mechanisms yet unseen. Hurricanes, in this context, are not disasters. They are expressions. The planet is trying to vent its fever. And just as volcanoes once ended the Snowball Earth by filling the sky with greenhouse gases, humans now play that volcanic role, not by accident of nature, but by the choice of civilization. Every action we take, burning, building, consuming, becomes part of the planet's thermodynamic story. The question is no longer whether Earth will rebalance itself. It always does. The question is what kind of balance it will choose next, and how many of us will still be here to see it. Part 13, The Human Equation. Technology, survival, and the race to adapt. The story of the Earth has always been one of adaptation. From single-celled organisms surviving beneath ancient ice to forests reclaiming continents after cataclysmic eruptions. But now, for the first time, the power to adapt rests in human hands. We are not mere observers of climate chaos. We are both its cause and its only potential remedy. Humanity stands at a threshold. The forces we once considered acts of God, storms, floods, droughts, heat, are now increasingly linked to our own machinery, our own progress. The question that once belonged to science fiction has become immediate. Can technology evolve fast enough to keep civilization ahead of the climate it has unleashed? Around the world, that question is driving an unprecedented transformation. a scientific arms race against the planet's own feedback loops. In vast research facilities, supercomputers simulate the entire Earth system down to the scale of clouds and ocean eddies. These models run trillions of calculations per second, predicting the paths of hurricanes, tracking carbon movement, and testing possible futures. They reveal not one Earth, but many versions of the planet shaped by the choices we make now. Dr. Gavin Schmidt of NASA's Goddard Institute calls it time travel through data. We can't change the past, he says, but we can explore the futures we still have, and those futures diverge sharply. In one, humanity continues on its current path. Fossil fuels dominate, deforestation accelerates, and feedback loops spiral unchecked. The result is a world defined by extremes. Megastorms, unlivable heat, and coastal cities slowly drowned by rising seas. In another, technology turns inward, harnessing renewable energy, restoring ecosystems, and drawing carbon out of the sky. The planet stabilizes, but at a new equilibrium, warmer, wetter, unpredictable, yet survivable. For now, both futures remain possible. The challenge lies not in invention but in scale. The science of clean energy exists: solar, wind, fusion, and carbon capture all work in principle. What remains is the will to implement them before time runs out. In the deserts of Morocco, fields of mirrored panels focus sunlight onto towers that generate steam and electricity day and night. In Iceland, geothermal plants draw carbon dioxide from the air and lock it into stone, turning pollution into rock within years. Off the coast of Scotland, turbines spin in tides so strong they could power entire cities. These are glimpses of a new industrial revolution, one designed not to conquer nature, but to cooperate with it. But even as these innovations spread, the storms grow stronger. Hurricanes that once struck once a decade now come every few years. Entire island nations prepare to evacuate permanently as sea levels rise. Droughts push millions toward famine and migration. Dr. Katherine Hayhoe, a climate scientist and communicator, warns that adaptation without mitigation is like mopping the floor while the tap is still running. She believes the real test of technology isn't how powerful it becomes, but how quickly it can help us change our behavior. Because no invention, no satellite, no reactor can stop the physical laws that govern this planet. Energy must go somewhere. The only question is how much we add and how fast. In cities like Rotterdam and Singapore, engineers are redesigning urban life to coexist with water, building floating neighborhoods, absorbent parks, and storm surge barriers that move like mechanical seashells. In Bangladesh, farmers are growing salt-tolerant rice on floating gardens. In the American Midwest, new wind corridors stretch from horizon to horizon, feeding clean power into the grid. These are not utopian projects. They are survival strategies. And yet, there's a deeper shift underway, a cultural awakening. For centuries, humanity saw itself as separate from nature, a force above it. But the climate crisis is dissolving that illusion. The hurricane, the drought, the thawing permafrost, all are reminders that the boundaries between human and planet were always an illusion. In a sense, we are living through the same process that once revived the frozen Earth. Then, volcanic heat restored balance. Now, the spark must come from us, from intellect, empathy, and imagination. Technology alone cannot save us. But without it, survival would be impossible. We have begun to design machines that mimic the planet's own resilience. Artificial trees that absorb carbon like forests. White roofs and reflective pavements that imitate the cooling power of ice. Satellites that monitor the Earth's heartbeat in real time, mapping its heat, its winds, its water. Each invention is a form of dialogue, humanity speaking back to the planet it has disturbed. And yet, adaptation has limits. No barrier can hold back a rising sea forever. No algorithm can rewrite thermodynamics. The deeper solution lies not only in technology, but in perspective, in remembering that the Earth does not need saving. We do. The planet will survive in one form or another. The question is whether our civilization, our art, our cities, and our children's futures will survive with it. As the 21st century unfolds, we face a test that no species has faced before: the ability to consciously steer the climate of an entire world. The same intelligence that built machines powerful enough to alter the atmosphere must now learn to restrain itself, to rebuild balance instead of breaking it. And in that sense, the race is not against the storm. It is against ourselves. Because if hurricanes are the Earth's way of releasing energy, then perhaps our challenge is to release wisdom before the planet forces us to learn it the hard way. Part 14. The Edge of Equilibrium. The planet's final balancing act. Every system in nature seeks balance, but not all balances are gentle. Some are born in violence, forged in extremes. The Earth has always been a self-regulating organism, constantly adjusting, cooling, heating, and cycling energy between its many layers. But even self-regulating systems have limits. Push them too far and they stop adjusting, they snap. Scientists call this threshold the tipping point, the invisible edge between stability and transformation. Cross it, and the world doesn't simply change a little. It becomes something else entirely. For decades, the idea of planetary tipping points was theoretical, a topic reserved for academic journals and climate models. Now, it has become a living reality, one we can measure, map, and feel. At the poles, the ice tells the story. Once, it reflected sunlight back into space like a mirror, cooling the planet. Now, as it melts, it exposes dark water that absorbs heat. The feedback loop accelerates. In Greenland, scientists have observed meltwater carving rivers into the ice sheet, tunneling miles down to the bedrock. The ice is no longer simply melting, it's disintegrating from within. Dr. Marco Tedesco, a glaciologist at Columbia University, describes it as watching an organ fail in real time. Each summer's melt triggers the next, weakening the ice's ability to recover in winter. There's no pause button, he warns. Once the system starts to run away, it doesn't stop. The same pattern appears in the Amazon rainforest, once the planet's greatest carbon sink. Deforestation and warming have pushed vast regions into drought. Trees that once inhaled carbon now exhale it as they die and decay. In parts of Brazil, the forest is becoming a carbon source, a reversal that could accelerate global warming even faster. Meanwhile, beneath the Arctic tundra, ancient permafrost is thawing. Trapped within it lies twice as much carbon as in the atmosphere today. As the ground softens, microbes awaken and begin to digest the organic matter frozen for millennia, releasing methane, a greenhouse gas more than 25 times stronger than CO2. This release, once triggered, is almost impossible to stop. Each of these systems, ice, forest, soil, ocean, interacts with the others. When one falters, it destabilizes the rest. This web of feedbacks is what scientists call Earth's climate engine. And for the first time in human history, that engine is misfiring on multiple fronts at once. Dr. Johan Rockström and his team at the Stockholm Resilience Center identify 9 critical thresholds that define the planet's safe operating space. We have already crossed 6. Beyond them, the climate no longer behaves predictably. Storms intensify, oceans acidify, and ecosystems unravel. But tipping points do not only spell doom. In physics, they also represent opportunity, the moment when a system can reorganize into something new. The same principles that push the Earth toward chaos can also drive renewal if harnessed carefully. That is where humanity's narrow path lies, between collapse and adaptation, destruction and design. In this liminal zone, the edge of equilibrium, innovation becomes survival. New materials that capture carbon from the air and turn it into building stone. Ocean pumps that mimic natural upwelling, restoring marine ecosystems. Artificial reefs that calm waves and protect coasts from hurricanes. It is no longer about stopping change. It is about guiding it. Because the truth is, the planet doesn't return to what it was. There is no rewind button in climate. The Earth that supported the civilizations of the past, the one with stable seasons and predictable weather, may already be gone. What comes next will be a different planet with different rules. And within those new rules lies both peril and possibility. Some scientists speak cautiously of managed transitions, scenarios where humanity deliberately reshapes Earth systems to stabilize them, cloud brightening to reflect sunlight, giant mirrors in orbit, fertilizing oceans with iron to stimulate carbon-absorbing plankton blooms. Ideas once dismissed as science fiction are now debated in policy circles. Yet every proposed solution carries risk. Interfering with one system may trigger unintended consequences in another. Geoengineering is like performing open-heart surgery on a patient who's still conscious, says climatologist David Keith. You can't predict every outcome, and you can't afford a mistake. And so, we live on the edge between mastery and humility, between control and surrender. The storms remind us of that boundary daily. Hurricanes are not simply warnings. They are the planet's pulse, beating faster as the fever rises. They show us, in swirling clouds and surging seas, the same pattern that has defined Earth for billions of years. When energy builds up, it must be released. The question is not whether Earth will find balance, it always will. The question is what that balance will look like and whether it will include us. We are, as Carl Sagan once said, the way the cosmos knows itself. And yet, in knowing, we may also be the force that tests the limits of that knowledge. At this moment, humanity stands on the knife edge of planetary equilibrium, with one hand on the controls of its own destiny, and the other resting on the pulse of a restless Earth. The next few decades will decide which way the scale tips. Part 15. The Reckoning and the Return. How the planet rewrites itself. There is a rhythm to destruction. It builds, it peaks, it fades, and then something new begins. Every epoch of the Earth story has followed this rhythm, from the frozen stillness of Snowball Earth to the roaring chaos of the modern hurricane age. What changes are the actors: volcanoes, oceans, forests, and now us. The planet has always rewritten itself. It erases, redraws, and renews, not in defiance of catastrophe, but because of it. The deep truth that science has uncovered, and that humanity still struggles to accept, is that stability is the illusion. Change is the constant. We tend to imagine the world as fragile, delicate, easily broken. But the truth is more complicated. The Earth is not fragile. It is ruthless. It adapts by transforming. When ice covered the planet, it found a way to thaw. When heat scorched it, it found a way to cool. When species vanished, others rose. It always seeks balance, but balance, to the Earth, does not mean comfort. It means survival. And in that relentless pursuit of equilibrium, humanity has become both participant and catalyst. The hurricanes we study, the data we collect, the satellites we launch, all are fragments of a larger human attempt to read the planet's mind, to understand its patterns before it shifts again. And yet, in doing so, we are also reading our own reflection. Because the forces that shape storms are the same that shape us: pressure, heat, energy, motion. We are, quite literally, made from the same system we are trying to control. The more we uncover, the more humbling the picture becomes. We have learned to split atoms and sequence genes, to model the atmosphere and predict the birth of a hurricane. But all that knowledge leads us to the same realization, that we exist within a story we do not fully author. The reckoning is not the storm. It is the realization that we are part of it. Still, even in this awareness, there is hope. The same ingenuity that fueled our industrial revolution can fuel a restoration. The same creativity that built machines can rebuild ecosystems. Across the world, this restoration has already begun, quietly, steadily. Coral nurseries in the Caribbean grow new reefs from fragments, seeding life where bleaching once erased it. In Kenya, women's cooperatives replant forests that anchor rainfall and cool the land. In Iceland, engineers inject carbon dioxide into basalt rock, turning air into stone. These are small acts, almost invisible against the scale of planetary change. And yet, they are the proof that life adapts not just by instinct, but by intention. Humanity, for the first time, has the capacity to choose how it participates in Earth's next transformation. And perhaps that is what separates this age from all others. The Earth will survive regardless, but whether it becomes a place of renewal or ruin depends on whether we act as its stewards or its storm. In a way, we have been here before. When the planet froze, it found renewal in warmth. When it overheated, it found balance in ice. When chaos ruled, order returned, but always at a cost. Now, the same forces rise again, demanding their due. We are living in the pause between extremes, the heartbeat between imbalance and correction. What comes next, flood or renewal, collapse or adaptation, depends on how we respond to the lessons already written in the planet's deep time. Every hurricane, every drought, every shifting current whispers the same message. Energy must move, cannot be contained. If we refuse to channel it wisely, the planet will do it for us. The reckoning, then, is not an ending, it is an invitation. To live in harmony with a system that is larger than any civilization, older than any dream. To remember that we are not masters of the Earth, but expressions of it. And if history holds any comfort, it is this: the Earth has fallen and risen countless times. It has frozen and burned, shattered and healed. Yet through it all, it has never stopped creating. Life always finds a way to return. Even now, as storms grow stronger and the seas rise, there are seeds sprouting in flooded fields, coral polyps rebuilding reefs, and humans. Resilient, imaginative, restless, finding ways to adapt once again. Perhaps that is our truest role, not conquerors of the planet, but participants in its eternal act of renewal. Because in the end, the Earth does not end, transforms, and in its transformation lies our final chance, not to dominate, but to endure. Maybe, as one scientist said while watching a hurricane's eye through satellite feed, the planet isn't angry. Maybe it's just reminding us who's in charge. The winds will calm, the seas will settle, and once more, after the reckoning, life, fragile yet unstoppable, will begin again.